In this video, we're going to set up an event handler that will be fired whenever we create a new citizen in our entity system. This will allow us to listen to this event in our render component and then respond by setting up the necessary components for displaying the citizen in our application. By doing this, we can continue the practice of keeping our model, the simulation, distinct from our view, the Unity rendering components. We'll start by defining a static event handler in the entity system. This requires us to import the system namespace. We will name this event onCreateCitizen. In order to fully define this event, we will need another event_args class that holds the arguments we want to pass to our onCreateCitizen event. Let's create a new script in our event_args folder called onCitizenEvent_args. We can copy the code in the onMapEvent_args class and then modify it to quickly create our new class. We will first update the name and then replace the one public variable with a citizen reference. Now that we have the event_args class, we can complete our event handler definition. We will provide the class as the template parameter in the definition. We now have the event handler defined, so we can use it to fire the event each time we create a new citizen. For the second argument of the invoke method, we will supply a new instance of our onCitizenEvent_args class, and we will assign the new citizen variable to its citizen reference. Let's move to the world render component and begin writing the code that will respond to this event. First, we'll want to subscribe to the event by using our setupEvents method. We'll have to define a response method called createCitizenRenderData. Remember, this method needs to match the expected signature of the event handler. This means its first argument will be the object that fired the event, and the second argument will be the onCitizenEvent_args that we provided when the event was fired. To write this response method, we are going to need a new class that will hold references to the render components for each citizen. This will allow them to be held separate from the citizen class itself. We do not want to embed these rendering components into the citizen class because it is a simulation component. We want it to simply contain simulation data and logic. Let's call the class CitizenRenderData. It might even be a good idea to eventually move this class to a rendering folder to further reinforce its purpose, but for now we'll leave it with the other citizen components. This class will not inherit from MonoBehavior because it will simply hold references to the game object and animator components that are associated with this citizen. We will name the GameObject variable WorldGameObject and the animator component simply Animator. They will both be public since this class is essentially just a reference container. Now we can use this class to begin writing our createCitizenRenderData method in the worldRender component. The first thing we'll do is define a citizen reference to hold the citizen that was passed in by the event args. Then we'll create a new instance of our CitizenRenderData class. We're going to need to calculate the rendering position of our citizen based on their simulation position on the map. Our map is simply a 2D square grid, but to display the citizen we need to translate this into a screen position on the isometric tile map. This is where the grid component is going to become useful. Let's define a new helper method that will allow us to convert between these two spaces. We will call the method grid2world. It will take the x and y map coordinates as arguments, and it will return a vector 3 that represents the corresponding position on the tile map grid. There is a method in the grid class called cell2world that almost does exactly what we need. We first need to provide it with a vector 3 int version of our x and y coordinates. This will give us a world position that corresponds to the very bottom point on one of our tiles. But we want to display our entities as if they are standing right in the center of a tile. So we'll have to offset the y value of this vector by 1/4 of a unit, because the isometric tiles are 1 unit wide and half a unit tall. so the vertical center of the tile is 1/4 of a unit up from the bottom. If this doesn't make sense right now, you could remove the offset after we get the rendering working to see the difference. Now let's continue with our practice of writing an int2 overload for this method. Let's go back up to the create citizen render data method and use the grid to world method to calculate each citizen's render position. Let's take a moment to subscribe and unsubscribe from the onCreateCitizen event handler in the appropriate places before we finish the response method. We're also going to need access to the render settings scriptable object in order to finish writing the render data method. So let's define a reference to hold the settings object and then assign the reference in awake by using the resources.load method. Let's open up the class for the render settings object so that we can include a new section. We will call this section entities. And we will define one new float variable named entity spacing. We're going to use this new settings variable in order to make sure that all of our entities are placed at slightly different z values in the world. This is going to help us avoid a problem that is often called z fighting. This is where two sprites are placed at the exact same z value in the world, and it causes flickering when they are rendered because the order they are rendered changes between frames. In order to fix this problem, we are going to introduce a small bias towards the z value in the custom transparency sort access we defined earlier. We still want the y value to be the primary sorting axis, but we also want the z values to be taken into account. So we're going to set the z value of our axis to 0.1. This will be enough to ensure the y value still dominates, but the z value will have some effect. Let's go back to the render data response method now and put this into action. We're going to take the world position that we have calculated, and we're going to set the z value based on two factors. We will multiply the citizen's unique ID value by the entity spacing setting that we just defined. This is why we chose to start the IDs at 1 instead of 0. This way none of the entities have a z value of 0. So they won't fight with anything at 0 either. Now all of our citizens will be rendered with a slightly different z value based on their unique ID. This will ensure that they do not fall victim to z fighting. We now need to get references to our citizen resources in our world render script so that we can begin instantiating citizen prefabs in this method. Let's create a new setup method in our world render component just like we did with the setup tilemap resources method. We will name this method setup entity resources. We now need to define a series of variables that will hold references to our entity resources for use in this script. First, we'll include a game object reference that will hold the citizens object that we created to be the parent of all of our citizen entities. Now, let's define a dictionary we can use to hold references to all of the citizen render data objects we will create for each citizen. We will index this dictionary using the unique ID value for each citizen. This will allow us to look up the render data every time we need to render a citizen. Now we'll define a dictionary which will hold the prefabs we have for each nation type. This dictionary will be indexed by the nation enum value, and it will allow us to access the prefab game objects whenever we need to instantiate a new member of that nation. Let's assign these references in the setup entity resources method. First, we'll get the citizen's game object by using the static find method in the game object class like we have done many times. Next, we will instantiate the citizen render data dictionary, and then we will instantiate the prefab dictionary and assign the three nation prefabs at the same time. The prefabs can be loaded using resources.load just like any other asset that we have placed into our resources folder for runtime access. There is one more bit of setup we're going to do for convenience. It is possible to set the frames per second or FPS value for each animation clip by accessing the menu at the very top right of the animation window when viewing one of the clips. But this menu only offers a small set of predefined values to choose from, and it is quite tedious to do this if we want to change a large number of animations. Luckily, this setting is also accessible through the scripting API. In our Setup Entity Resources method, we are going to get a reference to the animator for each prefab, and then loop through all of their animation clips so we can assign a consistent custom FPS value to all of their animations. We could make this even more convenient by creating a render setting variable that defined a single custom FPS value for all of our animations, and then we would use that variable during this setup. Let's call our new Setup Entity Resources method in Awake, and then check to make sure our FPS values are being updated correctly. Here we can see that our animation clips now have an FPS value of 12 instead of 16, so everything is working nicely. Now that we have all of the resources we need, we can finish up our Create Citizen Render Data method. We're going to instantiate a game object using one of our prefabs, and then we'll store a reference to that new game object in the world game object variable of our new Citizen Render Data object. Each monobehavior component has access to an instantiate method with a variety of overloads for different situations. We are going to make use of an overload that sets a lot of the information for the new game object while it is being instantiated. The first argument for this method takes a reference to the original object that we are attempting to clone. In our case, this will be the nation prefab that matches up with the citizen we retrieved from the event args. The next argument is the position within the world where we want to place the new game object. Here, we can use the position vector we calculated from the citizen's position. The next argument is the rotation of the game object defined by a quaternion. We do not want our object rotated at all, so we can simply use the quaternion identity value which is built into the class. Finally, we can provide the transform component of a game object that we would like to set as the parent of our new object. Here, we will supply the transform of our citizen's game object reference. Next, we also want to assign the animator reference in our citizen render data object so we can easily control the animation of our citizen later on. We will simply use the getComponent method on the world game object reference we just instantiated. This will allow us to access the animator component that is attached to each of our prefabs. This is exactly the same approach we used when setting the FPS for our animation clips, except this time we're getting the animator component on our new cloned game object instead of the one attached to the main prefab. The last thing we need to do in this method is store the citizen render data object in the dictionary so we can access it again later when we need to update the rendering for this citizen. Remember, we're using the integer ID of the citizen as the key for this dictionary. There's actually one more thing we are going to do after we set up the render data for each citizen. We are going to define a play animation method that allows us to start one of the animation clips for our game object. To define this method, we are also going to introduce an enum at the top of our class that lists the different kinds of animation that are available for our citizens. We will call this enum citizen animation type, and for now it will have two values, idle and walk. Our play animation method will then take an enum of this type as its second argument. When combined with the citizen reference, this will provide us all of the information we need to start the correct animation clip. The first thing we'll do in this method is access the correct render data for the citizen whose animation we're trying to play. Now that we have the render data, we can make use of the animator reference we set up earlier. Each animator has a play method that takes the animation state name as its argument. We are going to build up this state name using all of the information we have available from the method arguments. First, we need to notice that all of our clips are contained in a layer that is named base layer by default. This will be the beginning of our state name. The rest of the state name is simply the name of the animation clip itself. Our clip names have three parts. The first part is the name of the nation for the animation, the second is the animation type, and the third is the direction of the animation. So let's build up a string that correctly matches the state name we want by interpolating a series of values from our arguments. The first value will simply be the nation of our citizen. When using string interpolation on an enum value, it will conveniently convert the enum value to a string automatically. Next, we will provide the animation type that was passed to the method as its second argument. And last, we will provide the citizen's direction value, which will also be automatically converted to a string by the interpolation. That's all we need to do. Now we can call this method to start any of our citizens' animation clips. So let's start all of our citizens in the idle state at the end of our createCitizenRenderData method. Alright, we should be able to see our entities on screen for the first time now. Remember, we set up an event in our entity system that is fired every time we create a new citizen. And then our world render component is subscribed to this event so that it can generate all of the rendering components we need to display the citizen on screen. The last thing we did was ensure the citizen starts with the correct animation. Let's press play and take a look. Okay, so we see all our entities on our map now, and it looks like we have a nice mix of nations, and they appear to be standing in random directions. The idle animation is just a single image repeated, so the animations also appear to be working correctly. In the next video, we will introduce movement states to our entities so they can switch between their idle state and their walk state.